Welcome to Get Your FRQ On. This is from the 2004 exam, Calculus AB, question number 4. In the question stem, we're provided with an implicitly defined function of x and y, and we are asked in part A to verify that dy dx is a given expression. To verify this, we'll use implicit differentiation. So we differentiate the expression x squared plus 4y squared equals 7 plus 3xy. Using implicit differentiation, we find that we get 2x plus 8y dy dx equals 3x dy dx plus 3y. Notice the use of the product rule with x times y. Then we collect our dy dx terms, factor it out as a common factor, and solve for dy dx. So simplifying, we get dy dx times 8y minus 3x equals 3y minus 2x. Dividing both sides by 8y minus 3x, we get dy dx equals 3y minus 2x over 8y minus 3x, which is the given expression. In part B, we are to show that there is a point on the curve with x-coordinate 3 where the tangent line is horizontal. Now, because we're only given that the x-coordinate is 3, we have to find the y-coordinate for this point. We have to verify that the point we find is in fact on the curve. Now, if the tangent line is horizontal, that means the numerator of the expression for dy dx must be 0. We also know that the x value when that occurs must be 3. So if we set dy dx equal to 0 with the assumption that the x-coordinate is 3, that will happen when 3y minus 2x is equal to 0. But since x is 3, y is equal to 2/3 of x. Right, 2/3 of 3 is 2. So our point is 3, 2. If we evaluate dy dx at the point 3, 2, we do in fact get dy dx to equal 0. Now we have to verify that this point is in fact on the curve, the original curve. So verify that 3, 2 is on the curve. Well, if we substitute x is 3 and y is 2, the equation does turn out to be true. We get 25 equals 25. That shows that the point 3, 2 is in fact on the curve. The tangent line there is horizontal. In part C, we are asked to find the second derivative of y with respect to x at the point above and determine if the curve has any extrema there. Is it a local maximum, local minimum, or is it neither? So to find the second derivative, we use implicit differentiation on the expression for dy dx in order to find d2y dx squared. So we differentiate 3y minus 2x over 8y minus 3x. Note that this is an application of the quotient rule along with implicit differentiation. So by using the quotient rule, we get 8y minus 3x times 3 dy dx minus 2 minus 8 dy dx minus 3 times 3y minus 2x all over 8y minus 3x squared. Now, in the previous part of this question, we determined that dy dx specifically at the point 3, 2 takes the value of 0. We can use that to our advantage here. Since dy dx at the given point is 0 and we're trying to find d2y dx squared at that point, 3, 2, we know dy dx will be 0 there. That simplifies the expression a little bit. So when we evaluate this using x equals 3 and y equals 2, some of the terms will cancel out, makes the arithmetic a little bit easier, and we get d2y dx squared at 3, 2 equal to negative 2/7. Now, since dy dx is 0 at this point, and the second derivative is negative, that means the graph is concave down at this point. So the graph should have a local maximum at this point P at 3 comma 2.